Hello, everyone, and welcome back. My name is Corey, and you're my rubber ducks for the evening. And this is the series of episodes where we are creating Tang, a custom programming language, a scripting language, really, from scratch, using the C++ programming language. Yes, of course, you use one programming language to write another, but Vim is our editor. We're doing this in a terminal window and using fundamental tools such as Flex, Bison, Google Test for our unit tests, and ICU for our Unicode handling. And yeah, I think we're on episode 96, and we've been doing a lot of optimizations around our opcodes, writing better targeted opcodes. And we're going to continue in that vein, but I think I've done like 6 or so episodes on that topic, and that's not a bad thing. I think, if anything, the overall, can I call it a product of what we've created, is a lot better. But I want to have a slightly different focus, and that is this time I want to start using some profiling tools to tell me where to look where to look to do some work. Okay, so to find optimizations, that's what I meant to say. All right, if we go to our code, on the right-hand side, I'll just go ahead and do our make clean, make test watch. Okay, so that's going to be compiling on the right-hand side. On the left-hand side, what do we normally do? We say get log. We see the last commit was the end of episode 95. You saw that. And if I say get status, there are no files already done. I'm not following a script. I haven't pre-written anything. You're seeing me work live. I say there's nothing up my sleeves, right? This is 100% live coding. So you see this file here listed, this Callgrind out.1 before underscore changes, and maybe I didn't need to call it .1, but it's not in the Git repo, but I created that a while back, but it was before I started the optimizations. And we're about to compare that with the end of episode 95. How about that? As soon as this gets done running. And this is, we're checking against, it was the Fibonacci program. Yes. And so we've got all of our tests passing. Whoops, I'm in the wrong window. And if I were to run, for example, time build apps tang -s and feed in fib.tang 0.716, okay. And I think sometimes we're down below 0.7. We'll see. I need to pull up a little cheat sheet that just has my commands that I usually run. And specifically, that's the one I'm going to run. So Valgrind is a command line tool that it's meant for profiling your data. And we're telling it specifically we want to use Callgrind. And it's going to save this Callgrind out file. And then we will use KCachegrind, and that means process ID. So it'll be callgrind.out. and then whatever its process ID number is to visualize it. So let's do this. Let's run Valgrind tool is equal to Callgrind, and everything else is right. And now this will take a little while because it is, it's running some stuff. I'm going to capture one piece of information though, and that is right here. Episode, what are we on? 96. Callgrind references count. How about 1? Because we're going to do this a couple different times. It's still running. Oh, there we go. That's the number I want. Oh, wait. This. Sure. That's a little nicer to look at. And what is this? This is the, I guess, number of references that it is counting, and we want that to go down. But realize what we're looking at. 11 billion. 11 billion references are being thrown around. Okay, so if we now look at the files, we've got this callgrind.out. Let's move that to callgrindout2 to be callgrindout2 dot ep96 start. Okay, now I've got these two files, and the program KCachegrind is, I installed it with, and I think I've mentioned this before, where I did basically sudo apt install KCachegrind. And of course, if I try to do this, well, I messed up my password. It's going to say it's already installed. That's fine. But KCachegrind allows us to visualize the information that was collected. And I don't know what the reference number is with the first one, but this will, again, just let us, it's a number that we're going to keep track of at least for today. So KCachegrind, callgrind out, let's do 1 before changes. Okay. Can I also, at the same time, go KCachegrind callgrind out 2 to compare them? And the quick answer is it would appear as though I can accept this. Okay. So look at the title. You'll see callgrind out 1, callgrind out 2. Okay? And I can't use any of my fancy tools to help me snap the window location, so you'll just have to bear with me for a moment. So this is the old one, this is the new one. Now the purpose of this is to kind of show me, or let me visualize what's taking up the most time. But the number of calls is something I care about. So this, when you see this as a memory address, that means, yeah, it doesn't know where it's from, but it could be because it's a function that was created. And we do create functions programmatically in garbage collected, but look at this. Originally, this is before we started these optimizations, we were making 63 million calls to the garbage collected destructor. And we are now at 47 million calls to the garbage collected destructor. And by the way, here you can see on the right-hand side or on the left-hand side that there are calls to, and then this that ends in B50. And is that, oh, that's right here. That's the next one down. So what is this one? I don't know. I wish I could figure out what that one is. But you know what? That may be where we're creating garbage collected values. Could be. Because we create these anonymous functions. Oh well. But for right now, the 63 million versus 47 million. All right. We've been getting speed ups. And I've been saying, I mean, if we look at this, in the program execute, that's where we're spending obviously the majority of our time. Getting there isn't a lot of overhead. But program execute, and then within that, 37% is whatever this one is, and it's almost as popular as the garbage collected. So I'm thinking it is related to the garbage collected stuff. So if we can reduce the number of garbage collected, then I bet we can reduce, or even here, garbage collected 47 million. If we can reduce that, then we'll probably reduce the other, and that will make our program faster. That's my target. Okay. So now we can look and I guess see who is calling the destructor. So I'm going to close this now, just so we can, that was more, that's why I've been keeping that file around, is because I wanted to be able to compare. Source code Kali map. So this will just show us kind of where it's going. If I were to say in program execute, so the brown area over here, this area is the time spent in the execute function itself, not in other functions. I mean, the total, all of this is time in the execute function, but this is breaking it apart. So we've got a couple big areas, and that is within this right here, the garbage collected destructor. It's calling all of these things. So again, if we can reduce the number of times it gets called, and whatever calls the destructor. So there is, interesting. Okay. Sorry, I know I'm thinking, okay, that's what we want to do. And we're starting off at the number of destructor calls. I'm going to write this number down as well. And count one. Destructor calls, and that is 47119 Okay, you've got that. Now close those and let's start exploring. On the right hand side, we know we're going to have it compiling, so I'll get that going. We know that we're spending most of our time in the execution, and that's what's causing all of the destructors to be called. So the first thing is you may remember one of the early optimizations that I did was a single ampersand saved us a lot of time. So am I not using an ampersand where I should? So let's edit, we'll edit the test one just so we've got it. If we can No, 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 not test, because we're not looking at test. We're fib.tang. Okay, and what else? Source. Well, let's just do program execute. And if we need it, source, well, let's do include garbage collected and source garbage collected. Okay. Now this is our Fibonacci thing. So what are we going to be spending time on without needing to see the code? We know that we are return is going to be called a lot of times. That's going to put something on the stack, yeah, right? But this if statement, we haven't optimized our if. Okay, we might get some speed up out of that. N is less than 2. We have optimized that, right? So this is going to be a less than with an IS. So less than IS, LTIS. And then this is going to be a subtract. So it's going to be a subtract IS. And then this plus is going to be an add SS. And of course there's the function calls. Okay. But I want to, let's just pull the one that we're using the most, and that's the subtract SS. Subtract SS. What do we call? Not a lot. Binary op SS. Binary op SS. Let's grab it. Binary op SS. There. That's binary op SS. And I'm just saving it, making sure that everything still compiles and runs. All of our tests pass. All right. I mean, we haven't changed anything. Let's see. We are not using an ampersand here. Why not? Well, we had to pop off the right-hand side. Excuse me, so that we can get to the left-hand side and pop if off, and then push back this. Why can't we do ampersand? Because we're going to pop it off. Okay, so these are making a copy. Yeah, we've got a copy here on the right hand side, a copy here, and we're removing the originals, and then we're pushing back that. So that has to, so when we call left hand side minus right hand side, we are creating something, and then pushing it back makes a copy, but I'm assuming LHS minus RHS, yeah, that's gonna make, okay. Okay. I know I'm thinking out loud. How do we get, what's another way of getting to the stack? If I say auto top is equal to stack dot size, could I then say stack dot at top minus 1? And stack dot at top minus 2, and now what would that get me? Well, I'm no longer popping things off, but does that mean I wouldn't have to push it back? Could I then, okay, this is my memory failing, but let's do C++ vector reference. I know I can use this the square bracket. I don't think I want to use insert. Position. No, it inserts before. Okay. No. Oh, assign. Oh, no, that's for the entire thing. Yeah, definitely don't want that. Okay. I guess square bracket notation is fine for this. We'll do top minus 2 is equal to that. And now we would need to do stack dot pop back. Put that there. And now this could be an ampersand. And that could be an ampersand. So if I think through this again, that's just the size. Top minus 1, right hand side. Top minus 2 is left hand side. I'm reassigning stack number 2, stack of top minus 2, to be that. And then, so I'm only doing one pop, and I'm eliminating the copies, I think. Let's just, okay, so I'm saving. All tests are passing. Okay. Does fib still get the same thing? If I say looks like it's the same. Maybe. That got below 7. You know what? Let's run the cache, the Callgrind. So we want to get this number. Did we reduce the number of destructor calls? And did we reduce the number of reference counts? And while that's doing that, I want to stare at this code just to make sure I'm not doing anything wrong. Okay. Number of reference counts has gone down by 1,000,000. What about our destructor calls? Callgrind out.2.6 is actually going to become Callgrind out.3. Okay. KCachegrind of Callgrind out.3. Opened, of course, in different thing. And number of $47,119,529. Okay. $47,119,529. Wait. 119. 529. There's... How is it that didn't reduce anymore? Only that... Something doesn't seem right about that. You know what? We're going to try something. So we've got this, subtract SS, and we originally had something called, not this, but binary op SS, right? I think, sorry, I am having to turn on my outside lights because I forgot to. There, they're done. There. I think I would rather be able to pass in the LHS minus RHS and it be... That'd be the only thing. And I could delete those lines. And now, I think I could replace this with like the word expression. And then pass in expression. Caps lock. There. Wait. You know what? Let me follow this train of thought just for a moment. What I think is going to have to happen is I need to do that over and over. We've got for the add, subtract, we just did it. Trying to figure out a fast way of doing this, and it's not working. That's the modulo. Okay. Less than SS. Less than or equal to, greater than, greater than or equal to, equal to, I just don't want to. Ooh, does the period does a completely different thing. I don't think we can follow the binary op SS. Okay, so we'll have to fix it differently for the period. Index can do it. And what do we decide? Period. Can't use binary op SS because it will too soon. Yes. Oops, this one should go here as well. There. And instead of expression, it can be temp. Alright, now just need to remove these. Alright. Will all of this compile now? And will we pass all of our tests? All tests are passing. Okay. I want to run the Valgrind again. I don't think it's going to change anything because I only changed the SS stuff. No, it will. Because, oh wait, we were doing it with the add SS original. No, wait. How about this? Which ones are going to benefit from the SS? Only the addition. Why didn't I do SI? Excuse me, IS. Or was I doing... Evidently, I don't know what's happening here. But yeah, the SS is only going to be for the plus. Well, that's definitely not the biggest bang for our buck. Either way, okay, we've got... Okay. But, whoa. Okay. Three. Count 3. This is now 10, 7, 8, 7, 3, 3, 2, 2, 6, 4. Okay. That's significant. 2.7 is now going to be Callgrind out dot dot 4. Did I not do this earlier? Oh, 1 is before the changes. So I should change these numbers to be 2, 3, then 4. Alright, now let's figure out what this number is. KCachegrind of Callgrind out dot 4. Open, of course, in another window, and look at this. Number of destructor calls is down to 4,4,4,2,6,993. Okay, 3 million less. All right. I want to try something. Put it back on the make test. Up here, Again, we're just on the SS, but I've been doing stack at. What happens if we do this? Is it better? Only one way to find out, and that's to do this. We're about to get number 5. With that run. It may be the same, but we'll find out. 5. So if the number that pops up is less than 10,787,000,000, that's a good thing. We only changed it in the one place. We didn't change it the one where we had to do the one-off. Where we couldn't use our macro. That's what I'm getting at, yeah. This says it's more. $10,835. What about KCachegrind? Callgrind out dot. Well, it's going to be 2.9. I just didn't rename it yet. I just want to see it really fast before I abandon hope. $44,426,993. Okay, no change. Okay, that's fine. We won't keep. I'm not going to keep this one. Callgrind out dot 2931. Okay, so now we're back. Test watch, and we're going to. I'm guessing at is perfectly fine. You know what? I want to double check something. So at versus the operator. So at reference, a constant reference. If it is not, okay. Okay, so this does not check against the bounds, but because we are checking the bounds, I don't think we need at. It also returns a reference, but not a const reference. I think I would rather use the square bracket notation. Okay. And that means where's the one that had all the can't use blah blah blah. This one everything should still compile. We'll be fine. Okay, so if this worked, the other period SI, period II, is the only thing that's different on the period ones are what temp is equal to. Left-hand side, right-hand side. Yeah. Well, that could be abstracted away. Okay. Oh, it's... No, this in the middle might change. Okay, yeah, these are all one-off. Alright, let's go ahead and attack the next one then. So we're doing SS. That was for the plus. But I bet the n minus 2 is going to give us more bang for our buck because we call it more times. And, well, the n less than 2, those are both IS. So we're going to look for the IS ones. IS. You know what? We're going to go to the top. Binary up IS. We're going to pass in expression just like we did before. And now what do we need to do? We're going to say auto top is equal to stack.size. Do I need to do that? No. Because I could do auto ampersand, remove the pop, get the index stack, left hand side is that, and then can I do stack.back is equal to something? Sorry, looking for the right window. Back. A reference. Okay, so I'm wondering if I can do stack dot back is equal to expression. Alright, so we would stack check of 1. Don't need to get the top. Right hand side is a reference to stack.back. Left hand side is the bytecode. We check that the index can be reached. Do I need to perform this stack check if I'm performing the other one? I think not. Because left-hand side index is going to be 0, 1, 2, but that's an index. And if it doesn't exist, then okay, so yeah. In fact, if we just really want to be careful, we can say that. Now we just need to say what the expression is. Divide modulo less than or equal to, which are we using less than or equal to? I don't remember. Greater than or equal to, or greater than, sorry. It's greater than or equal to, sorry, this is something I just don't want to go on autopilot over. Okay, this one, gonna need some work. That's okay. But this one, that should work. Okay. Period is. Period is. There we go. I'm going to copy this. The stack value too soon. We may have to revisit how we're doing that, but all right, so temp is equal to that. Should it be move? Standard move. Let's just see if this compiles. Oh, it's allowing it. Okay, so it is allowing us to do the stack back. All right, and I think in that case, because this was IS, I want to say move. No, wait, it's an expression. Never mind. Okay, all tests are passing. That's a good thing. Let's call Valgrind. I always think it's funny how much my computer works during this time. The fan is so loud. There's a desk between the microphone right here and the computer down there. It's just really loud. All right. Look at that number. 10.2. Let's figure out the Callgrind. Move Callgrind out dot 3.1. It will be Callgrind out dot. What number are we on? 5. KCachegrind Callgrind out dot 5. Of course, it always opens in the other window. Oh, I told you that one was bigger. That was a bigger bang for our buck. I just meant to move that, but we're now down to 39,041,920. Okay. So that was worth it. That was definitely worth it. Now, the question is, if we, well, let's look at the fib. What else? It doesn't look like we've got any SIs or IIs, but we need to do those as well. We need to do the unaries. We need to, okay, that's fine. We're about to jump in. We won't worry about the unary. Let's do the binary op SI expression. And binary op II expression. So we've got SI and II. Okay. So I don't think we need to do the stack check of 1 because we're going to do a stack check here. Okay. We can call the ampersand. We're not going to pop. We are going to say the stack back is equal to the expression, and that's it. Okay. What about II? I just want to push back or in place. I bet you in place back would be better. And for that, okay. Let's do the SI one first for period. Because that one SI, okay. There we go. So this is getting the left-hand side, right-hand side. That's fine. Temp, okay. What else? Oh yeah. Get rid of those. Okay, that should be fine. Now for the II. Oh, there's II at the bottom. It's like, why am I not seeing this? Because evidently I've got issues. All right. I'm going to put the same comment, except it's going to be II. All right, we get our left-hand side. I think that's better. Well, that's better. And anything else that needs to happen? LHS, RHS. call that. All right, all of that looks right. I think add, or you know what? Let's just search for binary op. So we've got the add. SI. There. ZZ is what makes it jump to the middle of the screen. I did not know that until recently. So when it's at the bottom, hit ZZ, and now it's at the middle of the screen. But hey, that was one of the reasons for me using Vim, is because I just wanted to learn how it worked better. That's the period. Got all of those. There. Okay. Compile. See if it compiles. Cross your fingers. Hope all the tests pass. Bad function call. Huh. Did not expect that to happen. All right, so I don't have the tests. 1801. The bound function assignment does not change. Let's see what bytecode we're dealing with. Okay, null val, that's A and B. String hello world, string length. 13 is the string goodbye. Okay. 18 peak 2. That's going to be hello world. Poke that into 0. So that's assigning it to A, pop. And then a period on 0 and 3. So that's hello world dot length. So it's the II, and II is new, and period is the one that we had to deal with specially. So it's probably not in the compilation. It's just I needed to know what was causing it. And then, wait. 0, 3. Oh. That's when we call B. Okay, so this is, yeah, this is for bound functions, but it's probably in calling a.length. Bad function call. Let's look up period II, shall we? Wait, where is that happening? Now this failed in, so test. Okay. Does it say which test? Oh! It doesn't like that garbage collected. It's happening in a... So it's not about our code. It's probably about that move. Okay, that's fine. I wasn't trusting it, to be honest. Does that mean that we need to fix it up at the top? Opcode II. Binary op II. Oh, but we're doing an in-place back. That makes sense. Okay. That should have fixed all of that. Oh, and I've still got... Oh, I'm still getting a bad function call. period is. I betcha. I thought I had it in 2 places. Don't have it anywhere else, and this one is fine. So what is going on? Test.cpp 1839. Oh. That's in a completely different place. Still didn't get the right thing for 117. I think it was empty before. But this is 117. Okay, sorry. 1839, which is in executing this one. So everything was going great until an error shows up, and now we have to debug it. Wait, so does this mean it's I mean, not passing, but... So what is this doing? This is... Again, we've got this period II thing. Printed A, and A.length is 3. Why does it think we're trying to append foo? Well, not foo, but why did it append the word append? That's the name of the function that we're trying to call. Does calling the function use that binary op? So for program execute, okay, call func. That looks like it's correct. Is it call func? No, just call func. Not call func I. But there's the period underscore II is also showing up. Did I forget to pop something? Yes, I bet I did. Okay, so period II. We're not reading anything from the stack. So this should be an in place back. Or push back, right? And I don't know which is more efficient. Normally, okay, so what does in place back do? It takes whatever argument you provide and it calls the constructor directly. That will copy this, but so would saying pushback. Oh, everything's passing now. That's what it was. So just by way of review, SS will put we could do that and we could say stack back is equal to temp. So it removes something, and then because there are two things on the stack and one thing on the stack when it's done. Remove that dump. Go back there while I rerun the compile. And okay, so period SI starts with one thing on the stack, ends with one thing on the stack. IS starts with one thing on the stack, ends with one thing on the stack. II starts with nothing on the stack, ends with, well, I mean, these, but not removing anything, and ends with adding something to the stack. Okay. That, I believe, is correct. And now, after all of that, well, yeah, we're going to do our number 6. Valgrind. So this will be number 6 for us. Now, I think that this is going to be a lot less than previous because we're not really using these. But the call func, Number 6, I'm hoping for a lesser number there, lesser number here. Very fewer, 10, 262, 286, 795. Why? Because again, the majority of the work isn't being done on the ones that we're applying it to. Move Callgrind out dot 37, and we're going to call that Callgrind out dot 6. KCachegrind Callgrind out dot 6. It's on the other window. Move that across, and $39, $41, $920 didn't change it, but we know that it's going to be better for the others. Okay. Still, 39 million is a lot. You know what I'm going to do? I'm going to, at the end of the execution, see out this dump bytecode. You would never do this normally, but KCachegrind is running. I need to close that. I want to know what the bytecode looks like for Fibonacci. Of course, it printed out a lot of stuff, but Okay. Null val, jump, function. So creating a function, integer. Wait, and let's pull up the. So null val is fib. All right, and so jump to 37. What happens at 37? Function that starts at, or that takes one argument and starts at number 3. Okay, that's fine. All right, poke that into the first memory slot. So that's fib. Pop it. Integer 30. Call func I. 1, 0. So call func I. And look, call func I, call func I. Can we improve call func I? Call func I. What does it do? We get the position. We say the function is that. The arg count stack check. So function is already being, that's the one that's, we found this a lot earlier. And then we call func with function argc and all of this information. And we do this a lot. So let's look at call func itself. This is not a computed expression compiled. Oh yes, this is a argc. We have the right number of arguments. Keep going. We just push onto the PC stack and exit. And what's after all of this? Else if, else if, else if, else. Nothing, that's it. Not quite seeing anything else that we can do here. Position and do we not pop that? No, I is just a reference. Okay. So that's pretty efficient. just looking through the You know, I'm not seeing anything else that we can do for the moment. There, okay. Undo that. Now, rerun the make. So I don't think anything has changed, right? So we don't need to redo the Callgrind. And in fact, Callgrind out.6. And again, just kind of see where this puts us. So garbage collected is still a lot of calls to that, 39 million. Now this one's up a lot more. I'm wondering what, got to figure out what that is. 8D0. Who's calling that? Operator equal? Huh. Delete. And this, so I bet if we, remember we're still using our singleton object thing, maybe it's involved in that. But for this is what our, what our program is spending all of its time on. And this is the execute function. And the majority of time is spent in the destructor, in the, what is the, was that operator equal? Yeah. That's an assignment. And there's 6 million assignments. And who is calling all of these? This, whatever it is. Had to work more on that to figure it out. All right, let's kind of see where we are. Overall time. Let's see, we're on that here. This is kind of You know what though? That's not shabby. 0.629. That's pretty common. We're gonna grab that. And I'll remind you where we started, 791. So almost 0.8 and now down to hopefully close to 0.6. And I'll just remind you that we could that's all the recycles there. Wow, evidently I don't know how commenting works. And this is now just using not the singleton object pool or anything like that. Oh wait, is it? There. Now this, well, avoids the singleton object pool altogether. Doing a lot of rebuilding here. Just because I want to see the speed increase. There'd better be one after all this work. Of course, our garbage collected tests are going to fail. But if we do /build apps test, all of our tests pass, we're good. And look at that. 0.54 from 0.62. So another 50 milliseconds, you know. Well, in this case, 70 milliseconds. That's nothing to sneeze at. If we were to follow this, I just want to see if KCachegrind looks any different. Okay? Even though we're not going to keep this change right now, it's more just, seeing where we can go. By the way, we didn't implement this for the unary operations. So we could get more speed up just in general for unary operations, like not and everything, by... Okay, that's interesting. A lot fewer refs. Now only 8 billion instead of 10 billion. And KCachegrind, what? Callgrind, 4303. Other page. $39, $41, $9.22. So it didn't slow it down. Wait, and is this saying it's taking a larger percentage of the time? Maybe, but it could just be because other parts are faster and this is this didn't change. Could be. So now I'm almost to the point of thinking, is just calling it having it be a shared pointer and calling it good. Is that all that you would need? Another issue for another day. But we do see that there is a significant speed up for ditching the object pool. All right, we'll have to come back and visit that formally. But for now, Callgrind out.4303. That's fine. And let's undo all of these changes. Undo all of those. Let it remake. See what all differences we have in program execute. Binary op. SI, IS, II. And then just applying it to everybody. All of this is looking correct. Of course, the period ones are just ugly. We're going to say optimize stack pop push pop for binary op macro in program dash execute. Yay! We removed code and got better performance. That's always good. All right. Okay, so Callgrind are the only files that are present. That's all right. That's fine. Do I need to rerun the make? Actually, yes, I do. For the docs, because we changed our macros, which we need to write official documentation for those. I've just been putting it off because, well, it's easy to forget, and they keep changing. That's not an excuse, though. We should still write our documentation. We'll get there. Okay. For episode 96. Episode 96. All right, and one of the last things we do, again, hovering around 12.5. That's right, we had a net loss of code in this one. Always happy for that to happen. And this brings us to a good stopping point. I'm happy with that realization that we can save a lot of stack operations, and of course, we'll see that we've reduced our amount of destructors by, 8 million destructor calls. Out of 48, well, that's pretty good. Still some work we can do on timing. We know we can get rid of the singleton object pool. Do we want to do that? Are there better ways? Well, we'll have to think about it. There might be... Yeah, I'm going to have to think about it. I think the biggest problem is... Not the biggest problem, but... well, our use of nulls. Now, I mean, it's necessary, but can I get back to where we had the disassembly? Yeah, not disassembly. This is just the bytecode dump for Tang. We're not using nulls here. So what's taking all the time? Is it just the having to jump around and not being able to... in general, when a language is compiled, the opcodes are, or the instructions are located one after another. And while we do have a bytecode array, in order to execute the instructions here, it has to basically jump to another place in memory, and then it will have to jump to another place to execute the next bytecode, and it's impossible for the computer to be able to predict where that's going to be. So it kind of stresses the cache it's easy to run out of cache space. And of course, if this were compiled into machine code, the instructions would be sequential, right? It would just be reading one, then the next, and the next, and the next, and the next. And maybe that is, well, it would be a huge speed increase for us, but it's kind of beyond the scope of what this project is trying to be. So I'm just trying to think of what better tools we can use. The only other thing I can think of might be to how we, how we pull out our strings. Maybe do the same thing for all the constants, because we're having to create an integer 2, an integer 1. Do we do that in more than one place? An integer 2 here. That maybe we should pull out all the constants and that are being used. That might be something, because we would no longer be creating, have to create something and put it on the stack only for the next thing to have to pop it off the stack. And I think that is the secret. If we can reduce our push pops, yes, I'll leave it at that. I think that would be big. The question is, how can we do that without it being a lot of work? The problem is I just thought of something, a way of perhaps reusing the stack space for a compiled function. But again, that is beyond where we need to go. I think what we need to do is wrap up this video. And, thank you for joining me. And I'm sorry I ramble sometimes. I'm thinking out loud. Of course, you're my rubber duck. I'm talking to you. And at least let you know my thought process. No, we want to come back and we want to make sure that we're using this push pop optimization for our unaries, which I know we're not. If we say not something, we're copying it, or the negative of something, and probably a few others. And we still haven't optimized our slicing or some of our assignment stuff. So we can squeeze a little bit more performance out of there. But I think the biggest thing would be figuring out ways of not having to rely on that stack so much and pushing and popping. And maybe that's the issue. Maybe we need... So that's the thing. We don't... I said I was going to stop. We don't know if the slowdown is from code execution having to jump all over the place, or if it is in the stack pushing and popping. But the fact that the destructor is taking up, what was that, 39%, or not that much, but oh well. It makes me think that it's a stack issue. Okay, I'm stopping. Thank you for joining me, and hey, have a great day. Bye.